this setup here. No, why is mine not beeping? I don't know. But anyway, what are we working on tonight? Is this stuff you can verbalize?
Yeah.
Okay. What kind of stuff are we doing here?
So this is going to be like synthetic division.
Okay.
So the question is 2x squared plus x minus 10 divided by x minus 2.
Okay, so what goes in the box?
2.
Yep. The solution. In other words, if x minus 2 were a factor, then x equal 2 is one of the zeros. Now let's synthetically divide by just the coefficients. Let me draw that line down a little bit. What's the first step?
Bring the 2 down.
Okay, and then what?
Multiply 2 times 2 is 4. You get 5. You multiply 5 and 2 and you get 10. And you get the remainder is 0.
Okay, which highlights the zero remainder theorem also, which says that if x minus 2 is a factor of this quadratic, then this remainder has to be 0. And if this remainder comes up to be anything but 0, then x minus 2 is not a factor of that quadratic. And what is the result after you... In other words, what we essentially did there was we divided that quadratic by x minus 2. That's what we really did. And what did we get for an answer?
You get 2x plus 5.
Right. So it's equal to x minus 2 times 2x plus 5. That's how you would factor that. And we can see that that does work. It produces a plus x in the middle. Okay? What else?
The next one is 3x squared plus 7x minus 20 divided by x plus 5.
Divided by what?
X plus 5.
Okay. So tell me how to set it up. Whoops.
So you have negative 5 in the box thing. And then you have 3, 7, negative 20.
And just in, if you're missing a degree of the polynomial, you have to use a dummy variable with a 0. In other words, if it was 3x squared minus 20, then I would set it up exactly like this, only I would have to have a 0 there. Okay. So bring down that. What goes here?
Negative 16. Oh, 8. Negative 8. And 40. And the remainder is 20.
So x plus 5 is not a factor of that quadratic. But you can also do long division. Do you have to know how to do that, or?
I don't think so, no.
Okay. It's basically the same as synthetic, only you subtract instead of add each time. And with long division, we would get, if we divided that by x plus 5, which is what we're doing here, you do get 3x minus 8, but with a remainder of 20, divided by whatever your divisor is. So if you divided that polynomial by that linear factor, you would get that with a remainder of that.
Oh.
Okay?
Sorry, x to the 5th
goes across, what goes in the box?
1.
And what goes across the top?
1, 0, 1, 0, 0, -2.
Alright, I'll just do it. I know you know how to do it. What's the answer?
It should be
It's always going to be, the first term's always going to be 1 degree less.
1 x to the 4th.
Yeah, because you're dividing x to the 5th by linear x to the 1, you've got to start out with an x to the 4th.
And then x cubed, x 2x squared, x 2x plus 2.
And it is a factor, because of that 0. Okay?
This uses the rational zero theorem,
Okay?
and that's with all the possible zeros.
Okay. What's the polynomial?
F of x equals x cubed plus x squared minus 4x minus 4.
The rational factor theorem says what?
-4 is p.
Actually, what the rational factor theorem says is that if there are rational zeros, then the numerator of the rational zero will be a factor of the constant, and the denominator, q, will be a factor of the coefficient of the highest degree term. So my choices are plus or minus 4, plus or minus 1, plus or minus 2 in the numerator. In the denominator, I can do a plus or minus 1, that's it. So combining all of that, I got 6 possible answers that could be a rational zero. Plus 4, minus 4, plus 1, minus 1, plus 2, minus 2, and these are always plus or minus. Both P and Q are always plus or minus. Because minus 2 times minus 2 is equal to 4 also. Okay, so how do we start next? In other words, if we're actually seeking out a rational zero, what would our next step be?
Wouldn't you plug in one of the zeros and stuff like that?
Yeah, in other words, we would start with a number, start with the easiest one to do the math, and see if it results in 0. So I can do it a couple of ways. I would start with plus 1 and just substitute in. Well, that becomes 1 plus 1 minus 4 minus 4. Is that equal to 0? No. Let's try minus 1. Minus 1 plus 1 plus 4 minus 4. Excuse me. Sorry. Something went round the wrong pipe. Okay, that is equal to 0. Therefore, minus 1 is a solution. Now, I could also have tried it in a different manner by doing it synthetically. In other words, by dividing. This is actually called synthetic substitution, even though it's the same as division. Okay, I'm putting what I think is the 0 in the box, not the factor. The factor would be x plus 1, but the 0 itself, which I know is minus 1. Let's see if I produce a 0 down here. I have to if everything else I've done is correct. And I do. And the beauty of synthetic division as opposed to synthetic substitution is when I substituted -1 and I came up with 0, well, that told me that -1 was a solution, but it didn't give me the remaining factor. Whereas if I use synthetic substitution, I still decide that -1 is a solution, and I know that the next linear factor is that, based on this. So synthetic substitution is actually much better. I multiply x plus 1 times, excuse me, I didn't do that right. Right after I told you that term always has to be x squared. I mean 1 degree less. There. And even that isn't fully factored. Obviously that is equal to x plus 1 times x minus 2 times x plus 2. So had I continued on with the rational factor theorem, which I didn't really need to do once I found -1. In other words, -1 gave me the linear factor and it gave me the remainder. And in the remainder, because it was a quadratic, I didn't have to use that rational factor theorem. So the rational factor theorem is really more of a place to get started. It's to find one solution that then allows you to find the other two solutions. And you won't have many problems like this on a test, because if they were to make it reasonably tough, it's going to be like a 20-minute problem, because there's so much trial and error involved. Now, I do want to point out one thing. Notice we could actually solve that by grouping. We don't have to use the rational factor theorem, even though I know that that's what they specifically requested. But notice that if I group these two together and group these two together and then factor out the greatest common factor, see where I'm going here? Now I can factor out an x plus 1 times what's left over, x squared minus 4. In other words, I can get to that step much quicker than I can using the rational factor theorem. And that's because I happen to notice that the ratio of the coefficients in the first two terms are the same as the ratio of the coefficients in the last two terms. And whenever that's the case, you can group it. And it works, grouping it. And pretty much anything is easier than the rational factor theorem. Don't you agree? If there's an easier way to find the zeros of a polynomial, you want to do it. Anything but the rational factor theorem. It's such a pain.
Yeah.
All right. Can't quite understand you. Minus?
Minus 11x cubed.
Okay.
Minus x squared. Plus 19x. Plus 6.
6?
Yeah.
Okay. What are all the possible rational factors?
Plus or minus 1. Plus or minus 2. Plus or minus 3. Plus or minus 6.
Okay, that takes care of the numerator.
And plus or minus 1. And plus or minus 3.
Or you said 1 and my hand wrote 1. Okay, so what does that give us in combination? What are all the possible ones?
Plus or minus 1. Plus or minus 2. Plus or minus 3. plus or minus 6, and plus or minus 1 over 3, plus or minus 2 over 3, plus or minus, that's it.
That's it. In other words, the last two match the previous two. So there's our possible solutions. Have you had upper and lower bound yet?
What?
Have you had upper and lower bound?
No.
Okay. I won't go into that. So is that all you had to do for this problem, was just list the possible rational factors? Or did you have to try to solve it also?
It just says list all possible rational.
Okay. Because this one would be hard to actually determine which was a 0, and then we would be left with a cubic, and we would have to do the whole process all over again. So to actually solve this one would be quite a bit of work. But the way I would do it would be to start with plus or minus 1 and then try plus or minus 2. In other words, I would do whichever were the easiest numbers to try. I would leave these two for last just because the synthetic division is going to be harder, or the substitution is going to be harder with the fractions. Okay. What else you have?
4x to the fourth minus x cubed plus 5x squared minus 2x minus 6.
Notice that none of these terms have anything to do with the rational zeros. Only the two end coefficients. So possible numerators?
Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6.
Denominators.
Plus or minus 1, plus or minus 2, plus or minus 4.
And possible rational factors.
Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Plus or minus 1 over 2, plus or minus 3 over 2.
You know, I think that there's something to be said for being methodical here. In other words, the way I do it is that over that, and then that over that, that over that, that over that, and then I repeat. This over that, this over that, this over that. That way you don't skip any accidentally. Is that what you were doing actually? No. In other words, if we were doing that, I wouldn't have put that there. In other words, I would have gotten to 6, and the next thing I would have done was try that over each denominator. And that produces a plus or minus 1/2 over the 4. And then I try the next number over all three denominators. I already have that one. What's the next one? 3 over 2. And the next one?
3 over 4, plus or minus 1.
And then we got one more numerator. I've already got a 6, I've already got a 3, I've already got a 3/2. So that's the complete list. Does it matter if they're in order? I don't think it does. Probably not. Because it wouldn't make sense to have to do them in order. Doing them in order numerically would require you to jump around and mix everything up, and that'd be the surest way to miss one. All right, what else you got? It seems to me you know how to do that pretty good.
So, kind of the same thing for this factor the remaining polynomial.
Okay.
So x plus x equals x cubed plus x squared minus 4x minus 4.
Okay, that's the one we did, right?
Yeah, so we already did that.
Yeah, we already did that. That factored into x plus 2 times x squared minus 4. No, it was something else. But it was x plus 1. This answer was x plus 1 times x minus 2 times x plus 2. Right? If I remember right. I think that's what we came up with. Yeah, the plus 1 didn't work, but the minus 1 did when we tried it. Okay? What's the next problem?
2x cubed minus 3x squared minus 11x plus 6.
So we have to fully solve this?
Yeah.
Okay. Like I said, this could be a 20-minute problem. Is that what we want to do, or do you have other stuff that's giving you more trouble or more? I think you know how to do these. I'm happy to go through it with you. Is this the extent of what we have to cover tonight? Is solving cubics and quartics?
Does this really take 20 minutes?
Well, let's see. Let's see. In other words, first of all, it doesn't group. In other words, 2/3 is not equal to 11/6. So it doesn't group. So my next best method of solving it is the rational factor theorem. So let's go through all the factors.
Factor minus 1.
Here I can do the first 4 since we've had this problem. Okay. All over plus or minus 1, plus or minus 2. Did we do this already and we came up with plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 3/2, and that's it, right? No, what am I thinking? Plus or minus 1/2. In other words, the 1 over 2. Is that all of them?
I think so.
Okay. So, now we have to try them. So, let's see. Let's list our coefficients across the top. And what should we do? Should we plug it in to see if it's a solution, or should we synthetically divide or substitute? Synthetically works better because if it is a solution, we'll have the quadratic that's left over. Whereas if we plug it in, all we're going to determine is whether it's equal to 0. We won't know what's left over. And then we'll still have to do synthetic division. So actually synthetic substitution works the best because it's 2 steps in one. It gives you the answer if it is a solution. So what's the first one to try?
1.
Sure. Let's try 1. Go ahead. Give me the spots. I'll point and you tell me.
2, 3.
No.
-6.
No. 1 times 2.
Oh, 2.
Okay.
-1. -1. -4.
Done. I don't have to go any further. The moment I see that it is not a solution, I'm done. I don't have to come up with that number. I know that 1 doesn't work. Let's try -1. 2 minus 2. You watch and see if I make a mistake here. Holler. Is that a solution?
No.
No, it isn't. You just make sure I didn't make a mistake. -2 minus 5 plus 5 minus 6 plus 6. Okay? Next easiest, 2. You see how this might be a 20-minute problem?
Yeah.
And I don't know of a better way to do it. I mean, there is a thing called upper and lower bounds. That doesn't work right here. And upper and lower bounds does help a little bit, but I don't want to really get into it until you have it. This has promise. So, what is my linear factor and my remaining quadratic?
X squared minus 7x plus 3.
That's the remaining quadratic. What's my linear factor?
X plus 2.
Now, once you've reduced it to a quadratic and a linear factor, we're done. We don't need to use the rational factor theorem anymore. If I have to, I can, I don't have to even, because that factors nicely. Let's practice your factoring. What does that factor into? I'll get you started that far. What are the signs? No, both minus. In other words, when we examine that, that tells us the signs have to be the same, and they have to be whatever the sign of the middle term is. So it's minus, minus. Well, 1 and 3, I can either put 1 there and 3 there, or 3 there and 1 there. This produces a middle term of minus 7x. Minus x there, minus 6x there, add them together, minus 7x. So that means this is the correct factoring. And there's my 3 linear factors equal to 0. My solutions are x equal minus 2, x equal 3, and x equal 1/2. Which means I could have picked this one and solved for the first factor, or that one and solved for the first factor. But what did that problem take us? 10 minutes? No, maybe 5 minutes. But they're long, for sure. When they're cubics or quartics, they're brutal. There's one additional. Do you have any quartics to do? Do you have anything that says this is one solution, here's a quartic, what's the other 3 solutions?
I had some yesterday, but I already solved them.
Okay. What other problems do you want to do here?
I have no idea what it's called, but this is what it is, I guess.
Okay.
It's minus 7i.
What's that?
6 minus 7i.
Oh, complex solutions. Okay. And we're doing synthetic division?
I'm not. It's like, the whole problem is 6 minus 7i times 2 plus 5i.
Times what?
2 plus 5i.
Okay. So this is multiplying, adding, subtracting, and dividing complex numbers. Standard format of a complex number is a plus bi. Both of these are in standard format. A is 6, b is minus 7, a is 2, b is 5. To multiply them together, just FOIL them. What do you get when you FOIL them?
12 plus 38 minus 14i minus 35i squared.
In this term, any I that is to an even exponent turns into a real number. What is I squared equal to?
Negative 1.
So I'm going to multiply that by negative 1. And now combine the real terms and the imaginary terms to get your answer.
12 plus 16i.
What?
12 plus 16.
Okay, well, combine that and that. Those are both real numbers, so we can combine them. There you go. And that's all you do. And the only real tricky part is always converting the I squared that you get to a minus 1. Now, it's really easy to multiply and it's really easy to add and subtract. If I was adding these, I would merely add the real parts, add the imaginary parts, get that. So adding and subtracting imaginary numbers is a piece of cake. Multiplying, you saw, is pretty easy. Dividing is the only tricky part because it's not really division. If I give you this problem, 6 minus 7i over 2 plus 5i, we're not going to divide that. We're going to make the denominator a real number. And how do we do that?
Multiplying 2 plus 5i.
Actually, if we multiply by what's called the conjugate is just replacing whatever sign is separating them with the opposite sign. And since I'm multiplying the bottom by that, I got to multiply the top by that. And the reason I multiply by the conjugate is because it's guaranteed to eliminate the I in the bottom. Notice that that's the difference of squares factored. So 2 plus 5i times 2 minus 5i must be 4 minus 25i squared, since it's the difference of squares factored. And that turns into 4 plus 25, or 29. So we now have a real denominator. We're going to have an imaginary numerator. What was that? That was 47 plus 16i. So our final answer is 47 plus 16i over 29. So that's what that divided by that is equal to. And of course we might want to put that in A plus BI format, which would be 47 over 29 plus 16 over 29i. So division really isn't division. It's similar to rationalizing the denominator. If I said to you, how do we solve this? Well, you don't try to divide 1 by square root of 2. You multiply top and bottom by square root of 2, getting square root of 2 over 2. So what looks like a division problem really isn't. It's rationalizing the denominator problem. Same thing with imaginary numbers. It's not a division problem, it's a realifying the denominator problem. And that about takes care of imaginary numbers. There's not much more to know about imaginary numbers except for one thing. Then it repeats. Every 4 repeats. That's equal to I, that's equal to minus 1, I to the 7th equals minus I, and I to the 8th equals 1. So, what does I to the 500th equal? What? No, it's actually equal to 1 because 500 divides perfectly by 4. Notice that all of the ones that are equal to 1, the exponent is a multiple of 4. Since 500 is a multiple of 4, that's the same as I to the 4th or I to the 8th. Now, if I'd have said, what's 5I to the 503rd power? Well, that's the same as I to the 500th times I to the 3rd. Since that's 1, it's the same as I to the 3rd. or minus I. This is a problem that you probably would see on an SAT test or an ACT test even. But they would preface it by saying I is equal to the square root of minus 1. And you might also see that on your test. I don't know, have they covered this pattern of I?
Yeah, we covered it last year.
Okay, yeah. That's the only other thing about I that I know that's interesting. I mean, do you know how to, in other words, do you know how to simplify the square root of minus 48?
Yeah.
Factor out in other words, what I do with those every time is my very first step. I don't know if this is what you do or not, but my very first step is to factor out the minus 1. In other words, I turn it into that instantly because now I'm not confused about I anymore. Now I have to work with a real number and I'm going to follow it with an I. What else you got, Mina?
5 over 2 minus I.
What am I going to do with this?
Multiplied by 2 the conjugate.
Make sure you say multiply top and bottom, because the only thing I'm really allowed to do to any fraction is multiply it by the number 1. Any other number changes its value. I can multiply it by 1, and I can make my 1 look like anything I want. So my 1 is going to look like 2 plus I over 2 plus I. What's that turn the bottom into?
4 minus 8. 4 plus 2I minus 2I.
Those two terms always cancel out. So when you're foiling it, you only need to do the first and the last, because the two middle terms always go away. That's the reason we multiply by the conjugate, is it guarantees getting rid of those two middle terms. So all I really need to look at is the first and the last, which is 4 minus I squared, which is what?
Which is just 4 plus 1.
And the top?
10 plus 5.
And then simplify it and put it, well, simplify it, we'll put it into standard format. Simplifying what you see there.
2 plus 5.
Right. But if that was, say, a 4, that might lose you points if you gave that as an answer. If your teacher said, make sure your answer is in A plus BI format, how would we give our answer?
Wouldn't you keep it like that?
No, I wouldn't. In other words, that's not in A plus BI format. Split it up into two fractions. There's that fraction, and there's this fraction. So it becomes 2 plus 4/5 I. And notice that A is 2 and B is 4/5. And that's why they sometimes want it like that, because you can graph imaginary numbers, and you use the horizontal axis as the real axis, the vertical axis is the imaginary axis, and what you plot are those two numbers. In other words, when the real is 2, the imaginary is 4/5. So that point would be in this graph. That's the importance of A plus BI format, is it allows you to graph it a little easier. What else?
2 square root minus negative 49.
Negative 49?
Yeah.
Okay.
Plus 3 square root negative 54.
You're supposed to come up with the answer to that?
Yeah.
Okay, what do we got?
So you get 7i.
Hold on. That gives you 7i, but I got to multiply it by 2.
Yeah, 14i.
Okay.
Plus 8. Yeah, 8. So 24i. And equals 38.
Yeah, and that is in A plus BI format. It's just that A is 0. So that would be a sufficient answer. Okay. There are some interesting anomalies that happen. In other words, if I said, let's see if I can think of them. Hold on, I'm trying to think of what I was thinking of. Well, I can't think of it, so let's get back to your problems.
There's one is, wait. So you factor like a polynomial and then you find the, and then you graph it.
Okay.
So, f of that equals x cubed minus 2x, minus x squared minus 16x minus 20, given that x equals negative 2 is a root.
Okay, so x equal negative 2 is a root. So let's synthetically divide it, and we'll have what our remaining quadratic is. And then we can factor it. And then we can graph it. So x plus 2 is one factor. X squared minus 3x minus 10 is the other factor. How does that break up?
X minus 5 plus x minus.
Now, how does this allow us to graph it? It tells us the zeros. In other words, that gives us every place this function. Typically, a cubic looks like this. It has two extrema. Those are called extrema. They're local maximums and minimums. But the thing to remember is that cubics produce at most 2 extrema. Quartics produce at most 3. Quadratics produce only 1. Notice that a quadratic only has 1 local minimum or maximum. So a cubic, we're expecting it to look like something like that. So these points where it crosses the x-axis are huge. Let's figure out where they're at, and we'll be able to graph it once we figure out end behavior. Well, where are my zeros? At minus 2, plus 2, and 5.
Actually, it's x plus 2 squared.
Ah, x plus 2, like that?
Yeah.
Okay. So the zeros are at minus 2 with a multiplicity of 2 and at 5. So I know the function goes through the curve, through the x-axis there because the multiplicity is odd. And I know that it touches the x-axis here because multiplicity is even. In other words, it's going to do either this. It's going to do that or it's going to do this at that solution. Now, to determine whether the function starts like this or like this, we need to figure out what the left-hand end behavior is. Does it come up from negative infinity or does it come down from positive infinity?
Negative infinity.
Yeah, the highest degree term determines end behavior. We don't even have to look at any of this to determine end behavior. And you can tell if you substitute negative infinity in for x and cube it, you get negative infinity. So that tells you that it comes up from the bottom. So the start of this function, and it kisses the axis, it doesn't go through it because if it went through it, it would have an odd multiplicity, not an even. We also know that it's going to come down here and come back and go through that 0. And should look something like that. There's your two humps. I mean, you got an extrema there and an extrema there, so that fits. The only thing we don't have is the y-intercept. What's the y-intercept on this function?
I don't think we need to know the y-intercept.
Well, if they wanted you to graph it, it's nice to have that point. It's always the constant. Remember that the y-intercept comes when you plug in 0 for x. Y-intercept x is always 0. Well, when I do that, I get minus 20. So I happen to know that that crosses at minus 20. And there you have it. That's what it should graph like. Well, it's worth checking this end behavior to make sure I got my right-hand end behavior correct. And sure enough, if I plug in plus infinity, I get plus infinity. So the right-hand end behavior is correct also. So graphing these polynomials comes down to figuring out the zeros, figuring out whether it's an odd or even multiplicity to know whether it's going to cross through the x-axis at that 0 or if it's going to bounce off of it and just kiss it. And then find out your end behaviors because this could have looked something like this if my end behavior was different. In other words, put a negative x cubed as the first term and it's that graph, not the first one I drew. So once you figure out the zeros and the end behavior and how many loops you're going to have in the middle, that's all that you need. And remember, cubics can only have 2. This cannot be a cubic. In fact, that would be at least 1, 2, 3, 4. That would be a quintic by definition. There's a theorem that says the number of extrema can be at most 1 less than the highest degree of the polynomial. What else? We got about 5 minutes here. Do you have any final things you want to ask about? Want me to make one up and have you graph it?
Sure.
That will make it easy. Where are my x-intercepts?
2, -3, 4.
What's my left-hand end behavior? I'm going to come up from the bottom, and now what's my y-intercept? Multiply the three numbers together.
24.
Yeah. So up here at 24, now I know that I'm going to go through that 0 and I'm going to go through it, because the multiplicity of that is 1. Okay, I'm going to go up through my y-intercept, going to come back down through that 0, so some other loop, and come back up through this 0 and go on my way. That's a cubic, has two extrema. Left-hand end behavior is negative infinity, right-hand end behavior is positive infinity, which assures that it looks like this and not coming down from there, going through 2 there, and then back through 4 there. So it's all about your zeros, your end behavior, and maybe the y-intercept. Personally, I think the y-intercept is an important point here. And I don't know what this value is here on the y-axis. We could figure it out with a calculator. That wouldn't be that easy to figure out otherwise.
Yeah, they haven't taught us that yet. They said for calculus.
Yeah, I was going to say, that is a calculus problem. It's finding the first derivative and setting it equal to 0, and that would give you this point and this point. All right. What else? Anything else?
Not really.
All right. I will let you go.
Okay.
All right? Okay. Have a good week, Mina. I'll talk to you next time.
All right, thank you.
You're welcome. Bye-bye.